Hey, so in this lesson, we're going to study the properties that bonds and substances have. Let's get right to it. There's no bookwork associated with the lesson. The aim is what are some properties of bonds and substances that they make up. And here are your do now questions. We'll do these in class tomorrow. Just copy them down. All right, so I'm going to start off with a discussion of ionic bonds and their properties and the substances that are made of ionic bonds. But I need to start with the bonding pattern of Na and Cl. I'm going to, this is review up here at the top. I'm just going to skip right to it. It says, why does the radius of the sodium atom decrease as it forms an ion? That's because it loses orbitals, and the radius of the chlorine atom increases as it forms an ion because it gains electrons. But the really important thing on this slide is the question with +1 beside it. Why do you think the sodium and chlorine ions have sandwiched themselves the way they have? So here are my sodium ion and chlorine, or my sodium atom and chlorine atom. And you can see that the sodium atom decreases its radius as it becomes an ion as a result of losing an orbital. And the chlorine atom increases its radius as it becomes an ion as a result of gaining electrons from the sodium atom. But they sandwich themselves like this. And this is called a lattice structure. It's not on the Regents, but I'll write it in now. And these ions are forming a lattice structure because of the positive and negative attractions, but also because of the positive-positive repulsions and the negative-negative repulsions. I'll label some of the ions now, and that will help illustrate my point. So there they are. The reason why these guys are lining up the way they are is because, for instance, this negative ion is going to attract these two positive ions, which would then attract these negatives, attracting the positives, attracting these negatives, and all the way down the chain. And also, so that's not only is it maximizing attraction, but it's also minimizing repulsion. All right, ionic bonds are easily broken. The reason is because water has the ability to dissolve the ions. We'll call that property dissociation, and we also will use the word solubility. And I'll also draw a diagram to help you understand. But basically, ions are soluble in water, meaning they can dissolve, because the ions are able to dissociate from each other. And that's because they each have their own complete valence shell. And I'm highlighting that point with the dot structure up here. The brackets are indicating that both of these ions are stable. And that's the reason why it's possible for them to separate from each other and move in different directions. However, they would need a reason to do that, because in between these two ions you have some pretty enormous electrostatic attraction. But as I said, this electrostatic attraction can be broken if these ions are interacting with certain kinds of molecules, of which water is an example. So I'm going to add electrostatic attractions can be broken in the presence of water. And lastly, this process where the ions are broken by water, that process is called dissociation. So you might hear me say that the ions dissociated in class tomorrow. All right, so I'm going to draw a diagram to illustrate that point. It does involve a molecule of water, which you remember has a structure something like this. We have hydrogens down here, oxygen up at the top by itself, and it's asymmetrical because oxygen has 4 non-bonding electrons that push the bonds towards the other side. And since oxygen is by far the more electronegative element, it's going to have a slightly negative charge, whereas the hydrogens would have slight positive charges. So if you take these positive and negative ions, like this crystal, and you dump it into water, then the positive and negative charges are going to interact with the negative end of the water and the positive end of the water, and these ends of the molecule will stabilize the ions even further. So up here by the oxygen side, you're going to have all of the positive ions sort of attracting and congregating around the oxygen. And around the hydrogen side, you'll have all the negative ions that are more attracted down here, and they'll group up around the hydrogen side of the molecule. And for the record, assuming this is table salt, the negative ion is going to be the chloride ion, and the positive ion is going to be the sodium ion. All right, so that explains why ions can dissolve in water, because the polar molecule of water can stabilize the ion even further. All right, so I have some properties of ionic substances for you. Ionic substances are considered hard and brittle, and the reason is because if you are able to knock any of the ions out of alignment, you can create repulsion. I'll try to draw a diagram to explain that. So up here what I've drawn is I've just put the positives and negatives aligned oppositely so that you have all this attraction, and that high attraction between positive, negative, negative, positive, positive, negative, that's going to make the crystal structure very strong. So I put a check mark and a smiley face. But I did say that they were hard and brittle. Brittle means it's easy to break. So the reason why that happens is because the crystal structure, it's strong, but it also has a weakness, which is the same place that its strength comes from. So I'm just redrawing that left column right now, but what I'm going to do is I'm going to pretend that we've used a hammer or something, and we've struck the crystal here, but not on the left column. And what we've done is we've just moved the atoms down by the diameter of one atom, which is very small. So I'm just going to move that right-hand column down. And when I do so, that negative ion is lined up against a negative ion, positive is lined up against positive, and what you're going to get from that is a ton of repulsion. As these ions, like the two negatives right here and the two positives, start to line up, they'll have the same charge and they'll repel each other. So this one's very, very bad, and it gets a frowny face. And this is where the brittleness comes from, because this is going to cause the crystal to crack. So they also have very high melting points, and the reason is also just a result of the lattice structure. So the lattice structure is going to promote all of this attraction between ions, and therefore it's going to be very difficult to separate those ions, and that's why you're going to get a high melting point. And then of course the structure is definitely crystalline as a result of the attraction between ions as well. But this very last part about electricity conduction, that is tricky. And what I would say is that when ions are in their solid state, they never conduct electricity in any way. So I just recorded that in there. However, when those ions are dissolved in liquids, as we just discussed, or when they're melted, they are able to conduct electricity. The reason is relatively simple. The crystal structure, the lattice that looks like this, it doesn't allow electricity to flow because the ions are stuck in place. Electricity can only flow when it has this a mobile field of charges to flow through. So that's a really important idea. And this criterion is met if the ions are not in their crystalline structure, but instead have been melted or dissolved, just like it says in the bullet to the left. So both melted and dissolved, what you're doing is you're freeing up the ions, and those free ions are able to conduct electricity. So you don't need to take any notes on this slide, you're just going to hear a little bit of this video.
Many ionic compounds do not just exist in a laboratory or in your chemistry homework. Sodium chloride is regular table salt. Sodium fluoride is added to some toothpastes to help strengthen tooth enamel. Ammonium nitrate can be used to fertilize plants. Although their real-life applications are very different, they share a few key properties. In this lesson, we will learn about the properties of ionic compounds. These ionic compounds have very high melting points and are brittle because of their 3D giant ionic lattice structure. The strong electrostatic attractions holding the 3D lattice structure in place mean that a lot of energy is required to overcome these attractions. When we apply a force, it breaks the regular repeating pattern of oppositely charged ions, causing ions with like charges to come close to one another. The ensuing repulsion breaks the lattice structure. Sodium chloride, sodium fluoride, and ammonium nitrate can all dissolve in water, as we know. Or else we wouldn't be able to flavor our soups, brush our teeth, or fertilize our plants. Most ionic compounds are soluble in water. In water, an ionic compound can dissociate into its ions. So when we dissolve sodium chloride, it will dissociate into sodium and chloride ions. These ions become stabilized in water due to the polar nature of water. As you can see, the sodium ions are stabilized by the negative dipole of water, and the chloride ions are stabilized by the positive dipoles of water. This solvation stabilizes the free-floating ions. An ionic compound dissolved in water can conduct electricity. This is another key property of ionic compounds. This is made possible due to the presence of free-floating ions.
So that was a nice review of the properties of ionic bonds and their substances. We'll do a quick pass at the stability of covalent molecules before covering their properties. But really on this slide, the thing I want you to notice the most is that I have two molecules. You can tell because each of these pairs of atoms has an overlapping region, which I'm just calling an area of orbital overlap, but it's a place where their valence shells are being combined. So these are both covalent. And that's going to mean that at least between these two atoms, within the molecule, between the two atoms, there is super high attraction. So these two atoms are very much pulled together, but they're physically attached to each other by this covalence. Same thing here. This covalence is going to make very large physical attraction between the two atoms in the molecule. However, when you look in the space between the two molecules, you have no to low attraction. And most of the reason for that is because as these two molecules are just being molecules, what you're going to notice is that they're symmetrical. They don't have any slight positive or slight negative ends. And therefore, in between two molecules, it has just about as much attraction as two tennis balls would have for each other. They're relatively independent, discrete molecules with very little attraction between them. That's going to create almost all of the properties, which you'll see on the next slide. So molecules can be solids, liquids, or gases at room temperature. This is considered a property. And if they are solid, which is not all the time, but if they are solid, they're pliable, meaning that you can bend them without breaking them. This is the opposite of brittle. And the reason why that happens is because there is no crystal lattice within a molecular solid. And it's really the crystal lattice that causes brittleness. Similarly, since there is no lattice structure to enhance the electrostatic attractions between ions, these molecular solids are going to have very low melting points. In short, molecules are not attracted to each other and would be easy to separate. And assuming that these molecules are already in their liquid form, then the next thing I would say is that they would vaporize easily. They're going to change into a gas easily. It's what that means. And again, the reason is because molecules are not attracted to one another. And over here, you're just seeing some examples of different forms of molecular solids, liquids, and even within this guy's mask, which is made of a molecule, is probably molecular gas like oxygen. So molecular oxygen gas. This is, of course, rubber. Rubber is made of a molecular solid, and this is water, a molecular liquid. And again, we have some plastics down here, which are going to be molecular solids as well. Oxygen is gas. All right, you made it to the pair up. Just copy down this graphic organizer. We'll cover it in class tomorrow. Also, grab this summary. We'll cover it in class tomorrow as well. Thank you for watching. Have a great evening.